Okay, I'm back. Okay, I know it's a kind of boring. Really, it's too mechanical and tedious. Okay, but we have some time in maybe 5 minutes or 3 minutes maybe. Okay. Okay. So in general, the solution for this recurrence is of this form based on whether the two roots are identical or different, and these numbers will be determined from initial condition. For example, suppose this situation. So when n equals 0, what we have is alpha plus beta equal S0. And when n equal 1, we have alpha R1 plus beta R2 equal S1. So we need to solve a system of linear equations in order to find these values alpha beta. So you see everything to play. We need a linear algebra to solve system linear equations. I don't think even in high school, you may have learned this thing already. But anyway, it's important to remember the form. And the reason is why is the summation here? Because when the equation, the quantitative equation has two different roots, R1 and R2. The way our feeling is a solution will be of the form exponential function R to power n. But this value R can be two different ones, R1 and R2. And for this equation, it's easy to see that if this one is a solution and this one is a solution, then the summation is also a solution. From this recurrence, it's easy to prove. If we have two solutions, say let's see, maybe x1, x2, both are solutions. For this one, that will imply that x1 plus x2 also a solution. So that's why we have us here. Okay. Now for this one, when these two are same, then these two values have relation. AB has special relation. Because this special relation, what we have is the following. So X solution will imply that n times X are the solution. So this one is a solution. Will imply this one is also a solution. For this situation, then A, B are related. Okay, basically A squared minus 4B equals 0. First form. We have this relation, and this relation can be shown that whenever X is solution, this one is a solution. Of course, X will be of the form R to the power n of this form. So then this one is also a solution. So then the solution have two forms. One is this one is this one. Then again, this one is a linear combination of these two. So it will be of this form. This idea behind it. Why solution will be of this form when two roots are different, and of this form when these two roots are same. Okay? So it's useful to understand why it will have this form or this form. Basically, it's based on these property and this property. These two properties, right? Yeah, I know. Again, I have to admit, it's a kind of calling. It's an algebra thing. In a sense, it's straightforward but mechanical. Now let's have some fun. Okay, to solve some real problems. Maybe more fun. So I will give you two examples. Okay. So Fibonacci number, that's not so important and so famous. It would be nice to have a closer formula for this. Okay. Often people use capital F or lowercase f does not matter. It's easier to write it this way. So use a small case f instead of capital one. So it would be nice to have a closer formula for this one. If we look at this sequence, it's hard to imagine that the closure formula of this one will be complicated. Like from this, it seems to be very simple. But amazingly, the formula is very complicated, involving irrational numbers. So here, all of them integers. It's very hard to imagine that the closure formula will be involving irrational numbers. If I remember correctly, we'll see whether I get it right or not. We'll try to get this one. I think it should be clear. So see, it's very complicated. It's very hard to imagine it will be this complicated because this sequence is so simple integer. But here it's very, very complicated. And later on, I will give you another example. It's even more crazy. So it's very hard to imagine the formula will be this complicated. And it seems that's the best way to do. That's the formula. All right. So let's see how we can solve this one. All right. So let's see the characteristic equation of several equation is say r squared minus r minus n squared. That's the equation. So we need to find the root of this one. Somehow these are two roots. These are two roots. So these are two roots. So we get these two roots. All right. Now these two roots are different, and we know that solution will of the following form. In general, the solution will be of this form: fn equals alpha 1 plus square root of 5 divided by 2 plus beta 1 minus 5 divided by 2 will be of this form. Raised power to n, raised power to n. All right. Now we need to determine this alpha and beta. Use initial values. So what we know is these are initial values. Right? So we know that alpha plus beta equals 0. When n equals 0, so that's what we get. When n equals 1, we get equal 1. All right, so that's what we get. We need to solve this difference relation. It's tedious again. Now the problem involves this number. You have to be careful in order to get it correct. So from this one, we know alpha equals minus beta. Okay. So we can replace it. So for example, here, okay. So we can get this one. Using beta equal minus alpha, we get this one. See. Well, not too bad. I think we get both alpha and beta. Okay. So that's exactly what we get. Right? So yeah, so I think I got it correctly. All right. So see, it's basically what we need to do is to solve a quadratic equation, then solve a system of linear equations. Once we get, so we solve a quadratic equation. So to get the form correct, so we get roots. Then system of linear equations. obtain the coefficient of these two numbers. So basically, that's what we do in order to find the closing formula. All right. So we all know how to solve quadratic equations. I think maybe Wednesday we'll discuss some noise. I don't know where it comes from. I hear some noise, but then. All right. So it's actually it's rather surprising for such a simple sequence. Its solution is so complicated. The reason, I guess, is just because these two come from the characteristic equations, and roots for the characteristic equation of this is happen to be very complicated. So we don't have any choice because of this form. The amazing thing in the middle, all these things will be cancelled. It's hard to see that square root of 5 will be cancelled when we raise it to power n. For any n, actually, square root of 5 will not here at all. It disappears. So somehow it's used more than a symbol. In the intermediate step, we need them as a symbol. But we do not really use its value. It suggests because it does not really appear in the final solution. It will become more clear in the next example. Very simple example. All right, so from the formula, it seems to be very easy. It may happen that sometimes its characteristic equation has no real root. So what does that mean when characteristic equation has no real root? For example, if this is a characteristic equation, this one has no real root. So that means that sequence has no solution. What do we do then? This one has no real root, but it has two imaginary roots. Shut up! So in this case, actually imaginary roots, we need to use imaginary roots. Yeah, if someone is speaking or something. Someone say something. Who's doing it? Who's saying something? I don't know who's saying it. Seems everyone is muted. Yeah, I think muted all. Let me see. Okay, so I hope it's okay now. All right, so let's take a look at following sequence. Very simple sequence. Okay, is it simple enough? That's a sequence. Okay. Now, the term relation is also very simple. So this how the sequence say S, maybe just Sn. That's a sequence. All right. Now, remember this is the second order. Here we have Sn equal A, say Sn minus 1 plus B Sn minus 2. Here A equals 0. A can equal 0, but B should not be equal 0. Here B equal minus 1. All right. Okay. Now we can use the previous the formula to solve this one. So let's get its characteristic equation first. It's R squared 1 squared. So here is 0 times R minus 1 times R. So that's what we get. All right. Now this one has no real number as its roots, but it has two imaginary roots. R equals this is its root. So in this case, actually we use I as roots, I and minus I as roots. Then its solution will be of the following form. Will be of this form. This raised power to n. Okay, so it has two different roots. The solution will be of this form. All right, now we'll obtain alpha and beta from initial condition. So what we have is alpha plus beta equal to, and alpha I minus beta I equal to. So that's what we get. All right, now let's see what we get. So let's try to obtain alpha and beta. It's 10 alpha plus minus 8 2. If I sum them up, I get 2 alpha I equals 2 I plus 2. Right? So I have alpha equals I plus 1 divided by. All right. So alpha is this one. This is 1 minus I. So we get alpha equal 1 minus I. Then we can obtain B equal to minus this one, 1 plus I. So get both alpha and beta. All right. Now the solution will be this. But isn't it a kind of crazy for this simple sequence? We have this one as its solution. Actually, it's very, very difficult to see what this one gives us. Okay. So solution use imaginary number I. All right. That's actually kind of fascinating. This is some strange thing that comes in. It's very hard to imagine in advance. Really, the solution of this one will just complicated. It involves imaginary numbers. Very hard to imagine. Here, we only have actually two numbers, -2 and 2. But somehow the solution involving imaginary numbers. Here, the only difference is the sign changes, minus, plus, minus, plus. It's kind of oddly. But of course, for this one, an easy way to write solution maybe just Sn equal 2 or -2 based on modular form. One way is to write in this. Here will be 0 or 1. Here 2 or 3. Based on the remainder of n divided form. If 0, 1, then it's plus, otherwise minus. And now it's not, this one cannot look like a single formula. This one is a single formula. Actually, in this case, a single formula is possible because it's really what we need to control is to control the change of signs. It's not really from this one, okay? Control of signs. I think it's a formula. I think it's this one. It's a single formula. Instead of this one, if you once you see this, you're able to obtain this one. So based on single formula, there is this one. So this one is odd or even, control the sign here. So when it's by this condition, this will be even. Otherwise, for this, that's going to be odd. So it will control the sign. Minus one control the sign. But somehow the law of this imaginary number is just control the sign. This is therefore it's kind of oscillate. So you can see there is something unexpected when we deal with the sequence. Really depends on the roots. Okay. So only magic is the roots. Here the roots determine its solution. All right. So in general, we do have a solution for a homogeneous linear reconciliation or linear homogeneous reconciliation in general. We can extend the method for second order as follows. So in general, okay, so in general, we have linear homogeneous reconciliation. So in general, we have the translation of this form. We have to say Sn equal, let me see notation I use these. We have the translation of this form. It's a linear computation of previous k term. That's called linear. The linear comes from here. It's a linear combination of previous k terms. Homogeneous, each term has a previous term. Each term involving a previous term. So we don't have things like +3 or +n². We don't have these things. Otherwise, called non-homogeneous. We'll discuss it on Wednesday without these things. But that's only the foundation of non-homogeneous. In general, we may have these terms. All right. So every term will involve a previous term. And the constant coefficients, all these coefficients are constant, are real numbers. All CI are real numbers. So we need to deal with this kind of a translation. For example, we have maybe Fn equal 2 Fn minus 1 plus 3 Fn minus 3 minus 3 Fn minus 4. Right. So that fourth order linear homogeneous reconciliation with constant coefficient. So we need to deal with this kind of reconciliation. So luckily, we do know how to solve this reconciliation. And on the other hand, it's unfortunate in general, we really cannot do it by hand because in order to solve this reconciliation, we need to solve its characteristic equation, to find the roots of its characteristic equation. And to solve its characteristic equation is very difficult in general. We don't have a general way to solve it whenever k is more than 4. Now, even for 3 and 4, it's not easy at all. I forgot already use these formulas for 3 and 4. I only remember quadratic equation. I remember the formula. For formula 3 and 4, I forgot the formula already. Which I learned. I forgot whether I learned in high school or not. Maybe not. Maybe only second order equation, quadratic equation. But anyway, in order to solve this, we do need to find root of its characteristic equation. So what we need is to find the roots. So the roots of this formula determine its solution. So roots. And we know it's really very difficult to find roots of this kind of polynomial equations when k is large. Only for small k we know how to do it. Okay, so that means in general in homework or in exams, we will not go beyond k equal 2. So that if k equals 3, I perhaps will give you roots. Or perhaps as the equation is very simple, you can easily find the roots. Otherwise, no way. It's very difficult to find roots. All right. So suppose for this one we have roots. So let's see, we have t roots. Suppose the roots, we have t distinct roots. So we have R1, R2, R2, RT. All right, of course, this T is at most K. Each have multiplicity. So it's M1, M2, MT. Suppose that's the case. So that means this equation can be written in the form. So that by this actually means this equation actually equals this one. That's fine. All right, by this we mean after this equation is equivalent to this equation. So roots R1 is multiplicity M1. Roots R2 multiplicity M2 and so on. Suppose that's the case, then the solution of this recurrence is of the following form. It's very tedious when I give you the formula. So its solution is of this form. So it's a summation of term. Each term is of this form. So let's see, what do we mean? Each term is of this form here, where this one denotes a polynomial. This one denotes a following polynomial. And let me see the ordering. I forgot how to which way. I'll see. I don't know. In notes, I use alpha. So remind you again, notes is just to remind you what's going on. There are typos. Okay. And you may use different notations. So up to T1, here and T minus 1. So here is the T minus 1 and T. So this one denotes this polynomial. Polynomial degree T minus from let's see, for m minus 1, m minus mi minus 1. Okay, so it's a polynomial up to degree mi minus 1. So here is the root raised power to n times a polynomial of degree n minus 1. Maybe it's easier to write in words. Okay, it's a product of so there's a polynomial of degree n minus mi minus 1. Minus 1. So the highest degree here is mi minus 1. And see the coefficients. These need to be determined from initial conditions. So these are coefficients. To determine these, we'll need a system of linear equations. And by solving system of linear equations, we'll be able to find these things. You see, it's quite tedious. The important thing is to remember the form. No need to remember the notations. You can use notation. It's too tedious. Okay, don't remember the notation. Rather remember the form. If it has t roots, the solution will have these t roots, each raised to power n, so t roots. And then this part is a polynomial, depends on the multiplicity. Its degree is multiplicity minus 1. So if this root is, if this one equal 1, so this one equal degree 0, it's only a constant. Now these coefficients need to be determined by solving a system of linear equations. All right, so let me give you an example to finish today's class. You will see it's really tedious. So we cannot go too far for a larger k. So here maybe k equals 3. Let's consider one example. Let's see. Okay, 16. This equation. Yeah, okay. So initial condition is A0, A1, A. Because there are 3 terms, we need 3 values for initial condition. Okay, so value say equals 0, 1, 2, 0, 2, 3. All right. Now, its characteristic equation is r cubic minus 7r squared plus 16r minus 12 equals 0. You still remember how to solve this one? It's not easy at all, okay? I don't know how to solve it online. Luckily, I do have solution here, so I know the answer. I really don't know how to solve it online. I can try. You set out this one, 2, 2, 3, 2, 2, 3, 1, 2, 2, 3. So each one is tried. It takes time, maybe 5 minutes or more. I don't know. Okay. Typically, I may not get it. Okay, I'm too old for doing the tedious thing. It's a job for computer anyway. All right. Luckily, I know the answer. So the answer will be r minus 2 squared r minus 3 equals 0. Right. So that means it has 3 roots, 2 identical roots. 2, that's 2 identical roots, and another one 3. So I have 2 roots. One and 2 say if we want to spell it out, we have r1, r2, 1 and 2, another one 3. Here multiplicity will be 2. Here multiplicity will be 1. So here multiplicity. Okay. All right. So once we have this, then we know its solution is of the following form. For R1, this term is contributes the following term. R1 will be 2 to power, so let's see R1. So I don't think we need this thing anymore. Let's erase it. For R1, we'll have 2 to power of n, because 2 to power n. Then this one will polynomial of degree 1. So we have alpha n plus beta. Okay. All right. Now for this one, it's 3. So it's gamma, say 3. It's polynomial of degree 1, degree 0. Okay, let's see. Do I use alpha beta? Same as I use something different. Okay, you notice I use something different. Okay, so I will try to work online to see if you can get it back. You notice I use some different alpha beta gamma. Let's see. Or maybe better I change it. Maybe change it. Okay, otherwise you will get confused. Say this one alpha. This one is alpha. And let's see, beta, gamma. So use this one, beta, this one. So then it will be saying notes. Yeah, beta, gamma. Then that will be saying notation as in the notes. So then it's maybe better call this one is alpha as out to this one. Because otherwise, opening is not strange. It's not strange, and maybe I change it. Here, maybe change this one for R1. This R1, this R2. Okay. So what we need is to determine these three numbers, alpha, beta, gamma, using this initial condition. So we have its form already. It will be of this form. But these three values need to be determined. We obtain the correct form from the characteristic equation. And now we use initial condition to determine these terms. So then the TDS manipulation. All right. So let's see. So alpha equal sorry, for n equals 0, that's what we have. 0 give us alpha, so this one 1 plus gamma equal 0. Right? For n equal 1, what we get is 3 alpha. I think I like it. Then beta, here's 2, so 2 beta, 2 gamma equal 2. When it's equal 1, right? So here plus. When n equal 2, what we get is 9 alpha. Here the 2 is 4. It's 8 beta. 2 gamma. 2 and 4 gamma. So for each value, we have a linear equality. We have a equality, linear equality. So we have 3 of them. All right. Let's see. Do I get everything correct? When equal 2, it's 4, 8, 4. Okay. So I don't think I want to solve this system of linear equations, TDS. So eventually from this one, we can see alpha equals minus gamma. So it turns out the solution will be, I just give you a solution. Okay, the minus 5. So gamma equals 5. Beta. 2. Okay. So by solving this linear equation, this system of linear equation, that's what we get. The final answer will be an equals 5 times bn plus So obtain this one as our solution. Yeah, I'm just wondering, when they give you such a problem on exams, not much I can give. If I give this one maybe 10 minutes already to solve this one, right? If you careful, very careful, make sure everything is back. Could just take 10 minutes to make sure everything is back. So not much one can do for the exam, for midterm exam, I guess. That's the only contradict one. Oh, by the way, it's very difficult to determine time for midterm exam because it's not for my section. There are 4 sections. Somehow they want to coordinate everything. So that's getting different people have different opinions. We're still waiting. I don't know. Basically, towards the end of October, perhaps October 29 or something, last class or early November. I will let you know once it's determined. But certainly will not within 2 weeks. All right. Okay, so let's see. So let's finish our discussion of system of not just linear difference relations when it's homogeneous, but in practice, sometimes we need to deal with situations when the system of linear, sorry, the difference relations are not homogeneous. For example, consider the following. To obtain a closure formula for the square of first n numbers. It's not easy actually. Okay, one way to do it is to obtain a recurrence relation for this one. Then what we get is the following recurrence relation. It's very easy to obtain a recurrence relation. All right. Now we see that it's not homogeneous because we have this term here. We have this term here. All right. Now, if we look at this one, of course, we'll be able to solve it using iteration methods. We can try to use iteration method to solve this one. Now, eventually, what we need to do is to obtain a closure formula for this one. If we use the iteration method to solve this recurrence relation, what we need, actually, we needed to obtain a closure formula for this one. So it's kind of loop argument. In order to get closure formula of this one, we obtain this recurrence relation. But eventually, in order to solve this recurrence relation, we need a closure formula for this one. So that's not helpful at all. All right. On the other hand, it's rarely calls for solution for this type of difference relation. They are non-homogeneous. So that means some term so some terms cannot involve previous term like this one. How can we solve this one? We'll discuss it on Wednesday, all right, to see how we can deal with this situation. Again, the homogeneous is the foundation of this one. We do need to have homogeneous. Then we'll combine with particular solution for this part for obtain a solution. So we'll discuss it on Wednesday. All right, I think we'll stop here. Okay. So again, sorry, this part is kind of tedious and mechanical, but it's quite useful and important. I don't think you need to remember all these formulas, but rather you have to, you should know the idea behind it and the forms of a general solution. That's very important. All right. Okay. So see you on Wednesday.